Alright, so our new chapter is going to be on analytic manifolds. And so to start things off, just kind of a convention we're going to set up here is we're going to have K be a field complete with respect to a non-trivial non-trivial absolute value. First topic there is charts and atlases. Which is kind of how we set up a manifold if you haven't seen this idea before. So we're going to let X be a topological space. A chart C on X is a triple C composed of a set U, a function phi, and a value n, such that, first off, U is an open set in X. Secondly, n is a non-negative integer. Phone's buzzing, and also I forgot I was doing Roman numerals here. And thirdly, we have that phi from our function phi from U, our open set, to its image phi U, which is a set in K, and this set is open, and phi is a homeomorphism. And note on our notation here, U, we write U as O of C, as the open set of C. We have our phi written as M of C, as the map of C, and N be the dimension of C, which we call the dimension of C. I'm not going to write that out because I'm out of room and it's pretty straightforward. Let C be a triple as above, and C prime be another chart where we're just going to write our same three letters with primes next to them. Charts on X. Then C and C prime are said to be compatible if for V being the intersection of U and U prime, the maps phi prime composes phi inverse on the image of V, and phi composed with phi prime inverse on phi prime of V are analytic. So essentially we have our space V, like we have our we have our set X here, And we have one chart acting on some space and another chart acting on another space, and we need to make sure that the spot where they both act on makes sense, like the two different actions are compatible. And so this spot here is v. We have a function here, phi from v being the image of phi v, of course, in k to the n, and phi prime going to the image of phi prime of v in k to the n prime. And of course we just have our phi prime composed with phi inverse and vice versa. And we just want to make sure these two maps are compatible. And of course, if C and C prime are compatible, and this intersection is in fact non-empty, then the dimensions have to match up. A family Ci of charts on X is said to cover X if the union of their open sets is all of X. So essentially, if we have our shape here, I don't even know how to draw a manifold, something like, pretend this is some spooky shape. Essentially, we have one chart covering part of it, another chart covering part of it, probably with some overlap, and we can just that covers everything, so we can work with any given part of the manifold, assuming that everything lines up. Now, an atlas, this gives us the concept of an atlas. A on X is a family of charts on X covering X such that all the charts are mutually compatible. Oops, I can't even write today. Mutually compatible. Now we can compare our atlases here. Two atlases, say A and A prime are on X, are said to be compatible if equivalently their intersection is an atlas and if for any chart in A and any chart in A prime are compatible. And we note here compatibility of atlases is an equivalence function. Equivalence relation. What's an equivalence function? That's not a thing. Equivalence relation obviously reflexivity and symmetry are for free. to check transitivity, we're going to let A1, A2, A3 be atlases, and I'm going to pick a chart from Atlas 1 and a chart from Atlas 3. Now you want, of course, these two to be compatible. Now we're going to let V be the intersection of their open sets. If the intersection is nothing, then they are vacuously compatible by default. If V is non-empty, let Phi1 be the map of C1 and Phi3 be the map of C3. And by symmetry, we can just show that Phi3 composed with Phi1 inverse is analytic on the image of Phi1 of V at X. Okay. Sorry, I misread it here. At Phi1 of X for each X in V. Now we're going to choose a chart from our second atlas such that it contains the point we're looking at. Because keep in mind, atlases have to cover the manifold, so we have to have at least one chart like this. And then hang on, I think I messed up one little bit of notation here. I did not. They messed up a little bit of notation. I get it now. Okay. Well, first off, so taking an image in the intersection of U and V, mapping it through phi inverse, and then through our map phi in our second atlas, is a mapping from the image of Phi1 UV, that's what I meant before, from the image of U and V by phi, 1 to the image of U and intersect V by phi is analytic at Phi1x, and the map from likewise from the image of U intersect V under phi to the image of the intersection of U and V under Phi3. V is then analytic at phi of x. So we can kind of change what the function acting on x is with these maps. And thus Phi3 composed with Phi1 inverse, decomposed through these maps in the obvious way. Is analytic at Phi1 of x. So that's straightforward enough. Now I guess I should define what a manifold actually is. So start with the definition, the next section of analytic. manifolds. So we're going to let X, of course, be a topological space. An analytic manifold structure on X is an equivalence class of compatible atlases on X. Which, I mean, is kind of straightforward enough if you know kind of what's meant to be going on here, but let's give an alternative definition. Alternative view, just for clarity. Say an atlas A on X is full if whenever C is a chart on X whenever C is a chart on X such that C is compatible with every chart in our atlas, then C is an A. So essentially, our atlas contains every possible chart that is compatible with the whatever charts you want to assume are already in your atlas. So it's essentially just becoming maximal with respect to the charts, collection of charts in a topological space. Then, because of that, each equivalence class of atlases, I spelled atlases wrong, that's cool, of atlases on X contains exactly one full atlas. We can therefore define an analytic manifold so essentially we have this 1-to-1 corresponds between full atlases and these equivalence classes. So we can define an analytic manifold structure on X is the choice of a full atlas on X. And so henceforth throughout this in this chapter, X is a topological space with a fixed analytic manifold structure. With a full atlas of A of X. The chart C on X will be assumed to be belonging to our full atlas in question. Okay. So now fx is an analytic manifold, and x is an x. The dimension, the x dimension of x is defined, the essentially dimension at x of x is defined as the dimension of any chart C on X such that X is in O of C, in the open set of C. And it's called, as I said, the dimension of X at X. And so we have that the function setting each element of our analytic manifold to its local dimension is locally constant. On X, of course, if it is constant of, say, value n, we say X is everywhere of dimension n. Now there's some, and then of course when k is real or complex or periodic or a periodic number, we can say that we have a real analytic manifold or a complex analytic or a periodic analytic manifold. Alright. So lots of little chapters here, that's kind of good, makes it easier to pace out. Next up we have the topological properties of manifolds. So we're going to let x be in our k to the n, with of course n being an integer, non-negative, we're going to let r be a real number, which is of course going to be positive in this context. Then the ball b Rx, real ugly notation here, of radius r about x is the polydisk, essentially just uniform in all directions. We'll call it P of S of x, where S is just n copies of R. Now we're going to let B be a subset of X. B is said to be a ball if there is a chart C being the collection of U, phi, and N such that B is an U and phi B is a ball in K to the N. Then, first off, every point X in X has a neighborhood B, which is a ball, giving X as a locally a complete metric space. Hence is a bare space. Secondly, suppose that our base field K is locally compact. Then a ball in X is compact. In particular, if X is Hausdorff, it is locally compact. Third, suppose that X is regular and K an ultrametric. And each element X of X has a basis of Clopen neighborhoods. And we should probably go ahead and verify 3, because it's a little more nuanced than the others. Let B be a ball containing X, and C be a chart such that its open set contains our ball, and that our ball is actually a ball under its map. It's a ball in K to the N. And then, of course, phi of B is open in K to the N, so that B is open in X, as X is regular. There's a neighborhood V of X such that this is a neighborhood inside of B and V is closed in X. Then the inverse image under phi of balls in phi of V containing phi of X is a fundamental system of neighborhoods of X which are both open and closed. And yeah, you can see the appendix. And there is an example where this fails, where X is only Hausdorff. We're not going to go through it right now. But one last thing, maybe this won't be the last thing, but one more topic, because these are all shorts, is elementary examples of manifolds. Easily enough, first off, we have X being the discrete space. Of dimension 0, of course. Secondly, we have X being V, where V is a finite dimensional vector space over K, with the K dimension of V being n. Let A be the collection of charts, C as an open set, a function and a dimension n on V, where phi from V to K to the n is a linear isomorphism. The charts in A are compatible and of course cover, so A is an atlas. And from that you can find the full atlas, and you can give V the manifold structure determined by this. Third, we can let X be a manifold and U in X be open. And we can just shorthand our atlas as just A. We're going to define our A sub U to be the collection of charts in our atlas such that their open set is within U. Then A sub U defines a full atlas on U. The space U with this atlas is called an open submanifold of X. Number 4. Let X be a topological space and X be as the collection over an indexing set of UI. Suppose, first off, each UI is open in X. each UI has the structure of an analytic manifold. And thirdly, for each, that's not for each, that's there exists, for each I and j, the manifold structure on the intersection of ui and uj, induced by, of course, they're induced by the manifold structure of ui and uj agree. Then X has a unique manifold structure such that this restriction to each UI is given. Okay. And finally, number 5, we're going to let K be the reals. We will define a manifold X by identifying 2 copies of R everywhere except 0. And we're interpreting this as a quotient space. I'll explain how to do that in a second here. Well, first off, we consider R squared fibered by lines such that the collapse of the fibers, the quotient space obtained by collapsing the fibers, is R, is just our reals. Now consider R squared minus the origin and collapse the connected components of the fibers, which is essentially just our original fibers except for the one intersecting containing the origin, which is going to split into 2. Then we get the line with the origin doubled. And because of that, note that this is not Hausdorff. Alright, I mean, we went over time with our first video, so I feel like this seems like a fairly good place to stop. Yeah, next time we got all sorts of potential cool topics. Got morphisms on manifolds, products and sums, and germs, and tangent and cotangent spaces, all sorts of fun stuff. So look forward to that coming up. I'm going to call it here because it's a lot later than I normally like to record these, so I'm going to call her a bit early. Thanks for watching.